Hello everyone, my name is Chao Zhang from Old Dominion University. Today I will introduce our work, GALA, Greedy Computation for Linear Algebra in Privacy-Preserved Neural Networks. This work is co-authored with Chunsen Xin and my advisor, Hongyi Wu. First of all, let me introduce the background of machine learning as a service. Generally, there are often two parties, the client and the server. Usually, the client owns sensitive data and wants a referent prediction, while the server usually has a neural network that is trained with massive data and intensive computation. If the client is a doctor, he wants to send his sensitive data to the server, such that the server can return to him the private prediction. Here, the client doesn't want the server know the sensitive data, while the server doesn't want the client know the neural network parameters. So here the problem is how to efficiently enable such privacy-preserved machine learning as a service. In order to answer this question, let's first look at the structure of neural networks. When we take the convolutional neural network as an example, we can see that the neural network is featured with the interleave of linear and nonlinear transformations. For example, the convolution and dot product are two typical linear transformations, while the activation and the max pooling functions are two typical nonlinear transformations. In order to privately calculate the linear and the nonlinear transformations, there are generally three categories. The first one is based on the homomorphic encryption. The second one adopts garbled circuits, while the third one uses the secret sharing. Compared with the single primitive-based approaches, the hybrid schemes usually get better performance. Now let's go deeper into these hybrid schemes. From the state-of-the-art frameworks, we can see that the homomorphic encryption is a common choice in the linear transformation. Now let's see the H percentage in the total overhead. We can see that the homomorphic encryption takes large part of the total overhead in state-of-the-art neural networks. So it is a great potential to speed up the overall system by optimizing the HE-based linear computations. Now, let's go deeper into the HE-based linear computation. Given a plaintext vector, we can use the packed HE to first encrypt it into one ciphertext. As for this one ciphertext, there are three basic HE operations. The first one is element-wise addition, the second one is element-wise multiplication, and the third one is a permutation over ciphertext. Then we found that the runtime complexity of Perm is much larger than addition and multiplication. For example, our experiments show that one permutation is about 56 times slower than addition and 34 times slower than multiplication. However, permutation is imperative to enable the dot product and the convolution in the neural networks. So, in this research, we propose GALA, aiming to reduce the Perm in dot product and reduce the Perm in convolution. As for the dot product, if we calculate it in plaintext, given the weight matrix W and the vector X, we can just simply multiply each row of the weight matrix and the vector X. The final inner product can be obtained by summing up the elements. However, in the privacy-preserved machine learning as a service, the input X is encrypted. So, the problem here is how to efficiently calculate the dot product with this encrypted ciphertext. This is because directly summing up the elements in this ciphertext is not feasible. In the state-of-the-art GAZELLE framework, it first uses a column-wise diagonal encoding to first form two weight vectors. Then the input ciphertext is permed, such that the original ciphertext and the permed one can be directly multiplied with the formed weight vectors. Here we can get two intermediate ciphertexts. These two intermediate ciphertexts are added together to get another ciphertext, which has the partial sum of the dot product. This ciphertext is further permed such that its second half is moved to the first half. If we add them up, we can finally get a ciphertext whose first two elements are the result of the dot product. This ciphertext is shared between the client and the server in plaintext. Here we want to point out two observations. The first one is, if we first perm one ciphertext and then multiply it with a plaintext, it leads to a larger noise growth in the resultant ciphertext. The second one is, actually the permutation and the addition for the final ciphertext is not necessary. Based on the two observations, in GALA, we propose to first use a row-wise weight encoding to form two weight vectors, such that the input ciphertext can be directly multiplied with the formed weight vectors. Here we get two intermediate ciphertexts. One of the intermediate ciphertexts is permed and added with another one, which results in another ciphertext that has a partial sum of dot product, but with a lower noise. Instead of conducting the expensive permutations, GALA let the server directly generate the partial share of the partial sum ciphertext, such that the client can directly get the share of the dot product in a plaintext way. The server can also get its dot product share easily, as can be shown here. We call this kind of plaintext calculation as the client and the server as the perm-free share-RAS method. We can see that GALA can reduce the perm operations by this method and reduce the cost in the dot product. For the above example, we can see that GALA can reduce the perm operations by half, which results in nearly 2 times speed up. In general case, GALA can reduce the total number of permutations with a log term. In order to have a better understanding of the log term, we draw a figure about the number of slots in one ciphertext and the number of total permutations. From this figure, we can see that GALA can reduce the total number of permutations to 0, while GAZELLE will remain it at a certain level. So this gives GALA a potential to speed up the state-of-the-art neural networks with more neurons. So to optimize the dot product computation, GALA's row-wise weight encoding reduces the noise in the ciphertext. The details can be found in our paper. Next, GALA's perm-free share-RAS method reduces perm for final ciphertext to 0. For the convolution computation, GALA follows the similar idea in dot product. Here, we propose kernel grouping based on the number of channels in one ciphertext. So here, the number of channels in one ciphertext is 2. So the kernel is divided into 2 kernel groups, K1 and K2. As for kernel group K1, we first diagonally form 4 kernel blocks, such that each kernel block can be directly convolved with the input ciphertext. Then the convolution that with the same kernel order are added. Next, part of the convolution are permed and then added with the rest of the convolution to finally get the convolution result. As for the calculation for K2, similar idea can be followed. The result is shown here. As for the convolution computation complexity, we can see that GALA can reduce the most expensive permutations by Ci over Cn times. Here, the Cn is the number of channels in one ciphertext, which is relatively small because one channel will take certain slots in one ciphertext. The Ci is input channels, which is relatively large in the state-of-the-art neural networks. So this Ci over Cn will give GALA a significant speed-up potential. As for the performance evaluation, we conduct experiments in both LAN and WAN setting. We first download the code of the state-of-the-art frameworks, and then we plug in GALA and do the evaluation and the comparison. As for the dot product evaluation, we can see that the proposed shared RAS helps to largely reduce the dot product complexity. We can see from these dimensions that GALA only needs one ciphertext multiplication, while other works will involve a series of expensive permutations, multiplications, and additions. As for the time cost, we can see that the lightweight complexity leads up to 3 orders of magnitude speed up in the length setting. In the one setting, we can see that GALA's performance slows down. This is because the computation load is small and the communication load is large. Even that, GALA can still boost up to 4 times speed up. As for the convolution evaluation, we can see that our kernel grouping reduces the Perm complexity by over 50 times, as we can see here. And this dimension is a preferred dimension in many deep neural networks, such as the AlexNet. As for the time cost, we can see that our work boosts state-of-the-art frameworks by up to 14 times in length setting. In the one setting, our work still needs up to 8.7 times speed up with considerable computation load. As for the overall system performance, we can see that the proposed HE-based optimization reduces the Perm complexity by over 30 times, as we can see here. As for the time cost, our system boosts state-of-the-art frameworks by up to 21 times. In the one setting, we can also boost up to 24 times for the state-of-the-art frameworks. In conclusion, we propose GALA to reduce the Perm operations of HE-based linear computation in neural networks. We introduce a row-wise weight encoding and a shared RAS to reduce the Perm with lower noise in dot product. And we design kernel grouping to reduce the Perm in convolution. Both analytical and experimental results show GALA's efficient boost on the state-of-the-art frameworks. GALA can also be a plug-and-play module to accelerate other HE-based frameworks. Last but not least, it is worth pointing out that even with a significant progress toward privacy-preserved machine learning in recent years, including this work, there still exists a large performance gap between the plain-text system, generally below a second, and the privacy-preserved system, ranging from seconds to hundreds of seconds. Nevertheless, it is still promising to attain the long-term goal for practical implementation of privacy-preserved machine learning. First, the privacy-preserved machine learning system is to be deployed on clouds with abundant computation power. Hence, even though it takes significantly more time than the plain-text system on the same local hardware, running it on clouds with parallel computing infrastructure can significantly reduce the gap. Second, the research efforts and the in-depth optimization of the privacy-preserved computation further help to close the running time gap. Altogether, the combination of advanced algorithms and the cloud computation resources may enable the privacy-preserved system to achieve a response time well suited for some practical application in the near future. That's all for our work, GALA, Greedy Computation for Linear Algebra in Privacy-Preserved Neural Networks. And thanks for your listening. I'm happy to answer your questions.